Good day, again, grade 10s and 11s, and probably on this one, in these electric circuits, as well as the grade 12s. And welcome back to the Anti-Science Theory. Today, I just want to look at electric circuits because this has been a topic that a lot of my students as well as students that actually engage in the videos that I post. I've gotten quite a number of requests for on this particular topic. Um, so what I'll do then in this particular video and more videos to come, I'll try my very best, my utmost best to make this topic as easy as I can and as enjoyable as I can. Because once you understand this topic, you'll notice how amazing, very fun it can be. And it's not much of a challenge as we actually would most of you guys take it. So I'm gonna try to make it enjoyable to everyone. So I'll do the best of my abilities to make sure that this section just becomes one of your favorite sections, if not um not your least favorite and not your least not favorite or something like that. But anyway, okay. So for grade 10s it might be a new topic, and for grade 11s and 12s, I'm assuming that there are a few things that you must know and some that you might have forgotten. But I'm just gonna make sure I just go through everything just so we can just remind you just in case you've forgotten, right? So for starters, so I just want to talk about a few things. I mean, for every topic that I look at, I just want to go through a few fundamental definitions, right? So a few important definitions before I get into the depth of the topic. So for starters, what do we look at? We look at what we call current. So what is current by definition? So just a quick one there. So look at current. What is current? So current by definition, we say that it is the rate of flow of charge. So what I'll do is that instead of just writing the definitions, I'm just going to dictate them. And if you want to have them down, just repeat them these like two times or three, just so you can just write them down, because writing down is going to be quite a tedious task and very time consuming. I'm trying so hard to not to make this video long, but I'm trying very hard to make sure that it's comprehensible or whatever. Okay, so that is the rate of flow of charge. Right, so that's current, the rate of flow of charge. So as electrons flow, right, current is flowing throughout the entire circuit. And as current flows, the flow of current in a circuit tells us whether a particular circuit is either series or parallel. Remember those two terminologies, right? Right, and then we have the second one, which would be potential difference. Potential difference. I've been trying to learn French lately, or is it Spanish? Potencial. So whatever it is, I've been trying to learn that language lately. Um, Making good progress, by the way. So it's voltage or potential difference. So your teachers might call it voltage, and some might say potential difference. Those somehow boil down to the same thing. And then the third one would be resistance. Um, they really ask you to define this term in an exam, but just to be safe, we're just going to write down every important thing because we do not want to play with our marks there. Right. So what are definitions that we must look at? The first few definitions are current. What did we say? Current is the rate of flow of charge. And then we look at the other one, which is voltage. What is voltage? Voltage is the work done per unit positive charge. So by definition, voltage is the work done per unit positive charge to move from a single point, or rather from one point to another point, right? So that's what voltage is. What is it? The work done per unit positive charge. The work done per unit positive charge, right? So you could just rewind the video if you did not get that. So it's the work done per unit positive charge. And what is resistance? Well, resistance and current are known to be huge enemies. So these two guys are huge enemies. Nemesis, enemies, right? So what is resistance? Resistance is the guy that just doesn't want to see current very happy. So what does he do? He opposes the flow of current or the flow of charge, right? So that's what resistance is. Resistance is the opposition, right? Resistance is the opposition of flow of charge. So resistance is the opposition of flow of charge. So resistance is the opposition of flow of charge. The opposition of flow of charge. Like I said, if you didn't get that, you can rewind the video. Okay, so now that we've looked at that, I just want us to go through a few of these equations, right? So for current, let's just look at current. So current, what do you know about current? So current in a series circuit, I'm so sorry, I'm getting too hasty right now, getting too ahead of myself. So current, defined as the rate of flow of charge, is calculated by using this equation. So it's I equals to Q over delta T. So I equals to Q over delta T. That is current. Current is I equals to Q over delta T. So delta, we all know delta means change. So it's a change in time from the initial time to the final time, or from the final minus the initial. All right, so that's current. So current, you must know, calculated by this equation, right? And if you look at potential difference, or in this particular case, I'll just say voltage. For voltage is calculated by using the equation V equals to W over Q. So that is voltage. It is the work done per unit charge, right? And then for number three, we look at resistance, right? So resistance, I'm assuming that's French, resistance. Sounds a bit like Renaissance, Renaissance. I used to actually say Renaissance, and I actually found out recently that it's not Renaissance, it's actually Renaissance. But anyway, so that's voltage, resistance, and resistance is calculated like this. Okay, we'll get to what this actually is. In fact, let's actually do that now. So, we come across a law, I don't know how I did that, which we call Ohm's law. That was not meant to be straight. Ohm's law, very nice, and that's a very nice squiggly line. So what do we look at? We speak about Ohm's law. Ohm's, Ohm's, Ohm's law. Crazy how I've always been procrastinating. I've always wanted to just find out who exactly is this Ohm's guy they speak of. Was it actually a person? Was it not? They just come up with I mean, there's always some person behind the name, just like Newton's laws. We know about Sir Isaac Newton. I mean, grade 12, you look at chemical equilibrium, and we always know, okay, if you're talking about Le Chatelier, who exactly is this Le Chatelier? I just never got a chance to find out who Ohms is, right? But I'll do that as soon as I get time. You can also do that. I mean, research is just fun. Okay, so Ohm's law, why am I saying laws? It's only one law. So Ohm's law deals with this equation in particular. So that is R equals to V over I, right? So what does it actually state? So this I'm just going to write down. So Ohm's law states that the potential difference across the end of a conductor is directly proportional to the current flowing through that particular conductor, given that your temperature remains constant. So that must be maintained. So I'm just going to reiterate. So what is resistance? Oh, sorry, what does Ohm's law say? Ohm's law says that the potential difference that is the voltage, the potential difference across the ends of a conductor must be directly proportional, or rather is directly proportional to the current through the conductor at constant temperature, right? So the potential difference across the ends of a conductor is directly proportional to the current through the conductor, given that the temperature remains constant. So what does that mean? That means if I'm saying the potential difference, which in this particular case would be, oh, and by the way, before I get too ahead of myself, current, which is denoted by the letter I, right, is measured in what we call amperes. Amperes. So that is A. And then our charge here that we did, remember you were doing electrostatics? Yes. So charge here is measured in coulombs, denoted by the letter C, right? Coulombs, 5 coulombs of charge. Right, and that's a capital C, by the way. I know that kind of looks small. This should be capital C. And then time is well measured in well, seconds, because this is physics. We always make sure that our time is measured in seconds. Right. Big mistake that I've noticed, guys. Please do not make the mistake of not just in electric circuits. I mean, in any question on physics where you just have to calculate the time. When you get the final answer, please do not write this. So do not have something like, say, you calculated the time and you got something like 7 as your answer. This is 7s, or you could write 7 seconds. Do not do this. 7 sec. This is not an answer. This is wrong. Do not write 7 sec. So wrong. 7 sec is wrong. Do not do that. That is a very common mistake. So please try to avoid that at all times. It is not 7 sec. There's no such thing as sec. Right? So it's 7 seconds or 7s. Right. And then when we look at voltage, this is terrible, 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 terrible. So voltage is measured in volts, and that is denoted by the capital letter V. And W, E, sorry. So W is work, right? And that's like basically talking about energy. In fact, let me just write work. Right? So I mean, if you think about it, you need energy in order for you to do work, right? So energy, and that is measured in joules, capital J. I'm not gonna go through a Q because this Q is the same as that Q. And then for resistance, resistance is measured in ohms, denoted by that symbol right there. Okay, so these are very important things you must remember. Now back to Ohm's law. So what does Ohm's law say again? The potential difference across the ends of a conductor is directly proportional to the current through the conductor, given that your temperature remains constant, right? So that is the voltage. I mean, so mathematically, how you would represent that is that the voltage is directly proportional to the current. And if you look at this equation, R equals to V of I, what do you notice? Every time I decrease my current, the resistance actually increases. How do you know that? So if you take your calculator, for example, so this is how I usually check. So maintain a V. So choose some value of V, right? So let's choose a value of V. So for example, I say that V is 4 and it stays as a 4. So I maintain that 4 as a V. And then for I, let's say I take 2. So if I take 2 for I, so V remains constant, right? What do you think my value of R will be? So this here will be 2 ohms. But if I increase the value of I, given that the 4 remains the same, so I still have my 4, and I increase the value of I and I make it a 5. What is the value of R? So the value of R will then be, what's 4 divided by 5 last time, and that's supposed to be 0.8 ohms. And then again, I go again and I say R equals to maintain the 4, and, oh, sorry, um, consistency, make a very cute circle, something like this. Yes. So that's 4, and I divide it, say, by, um, let's go 7. What's the answer? So any 4 divided by 7, that should give me 0.6 or 0.57. So 0.57, two decimal places. What do you notice? So notice the trend. As my current gets bigger, so from 2 to 5 to 7, my resistance gets smaller and smaller and smaller. So as my resistance, sorry, my current increases. So it went from a 2 to a 5 to a 7. So it increased. What happened to my resistance? It dropped from a 2 to a zero point 0.8 and from a zero point 0.8 to a 0.75. So what does that actually tell you? That tells you that an increase in the resistance decreases the current. Similarly, an increase in the current decreases the resistance. So in that particular case, that tells me that my voltage is directly proportional to my current, and my resistance mathematically is inversely proportional to my current. An increase in my resistance decreases the current, or an increase in my current decreases the resistance. However, the voltage is directly proportional to resistance. This is only true in a series circuit. I'm going to show you why as we get into the different circuits, series and parallel. And just be specific. So the voltage is directly proportional to the resistance only in a series circuit. Only in a series circuit, right? So these are the three relationships that you actually deduce from Ohm's law. So the first one is that voltage is directly proportional to current, and then that resistance is inversely proportional to the current. A very, very, very important part. Right, so just to quickly get into the respective um, circuits, right? So I'm just going to get into the series circuit as well as the parallel circuit. So let's just quickly have those two parts here. So I'm going to have my parallel circuit here. In fact, let's start with the series. So I'm going to have my series circuit here as well as my parallel circuit here. So it's going to have a small drawing. So guys, remember, so if you have something like this, that is known as a cell, right? But if I introduce another cell right here, this is now known as a battery. So a battery is a combination of two or more cells, right? Okay, so I would have my drawing here. So I'm just going to underline that. Underlining is the best thing in the world. Okay, so I'm gonna have my battery right there. Ooh, ooh, okay. Oh, 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 oh. Okay, so I'm gonna have my battery, and then my circuit here. But I want to make this circuit very perfect. Um, just need to keep time intact. Okay, uh, so I'd have my ammeter here, A, um, my resistor here, say R1, um, my other resistor here, and okay, terrible, terrible, terrible. Okay, so I'm just gonna have something like this. Okay, so that's R2. And I'm gonna have another one here, like that. And my first resistor, R1, and my second resistor, R2. And they're gonna be joined in parallel like that. So I'm just gonna add my emitter here. Okay, just before I get too ahead of myself, please remember that an ammeter and a voltmeter, voltmeter. So what measures, so the current, which is the rate of flow of charge, is measured using an ammeter, right? So the current is measured using an ammeter, and the voltage is measured using a voltmeter. Okay, so what you must know is that in a voltmeter, in an ammeter, sorry, we have no resistance. There is no resistance in an ammeter. And with that being said, you must know that if there's no resistance, that means there is infinite, sorry, not infinite, but rather proper terminology would be more current. So there's a lot of current. So let's just make it maximum current. So there's maximum current in an ammeter. And in a voltmeter, there is actually the opposite. So there is infinite resistance. Infinite resistance. So there's infinite resistance in a voltmeter, and therefore means there is no current. Why? Because of the inverse relationship that we found out here. We said that if you have an increase in the resistance, you have a decrease in the current. So if you have infinite resistance, that just means it's just resistance on non-stop. So there's non-stop resistance. That means there's just zero current. So these are your two respective circuits, right? And then you just to quickly just separate these. I'm gonna have something like that. Underlining is the best thing in the world. Oh, my primary school English teacher used to love that song. I mean, we just used to be one of those people that just don't like underlining. Um, um, it was quite tedious if you ask me. I mean, it's just a waste of. I mean, we just find it as a waste of um time, I guess, or me personally. But I got used to it. You know, it becomes a very good habit. Okay, so what do we know? So what do we know about a series circuit? So just want you guys to know this. So in a series circuit, so we're going to start with the current. What do we know about the current in a series circuit? So the current in a series circuit is the same everywhere. So the current is the same everywhere. Everywhere. So the current in a series circuit is the same everywhere, right? So what do we know about the current in a parallel circuit? So in a parallel circuit, the current is divided. The current in a parallel circuit is divided, but not just divided. It's divided proportionally. Pro oh, sorry, not proportionally, but inversely. That was my bad. Inversely. So what does that actually mean? So that means in a parallel circuit, so let's just remove R1 and R2 and put in actual values just so you can understand this. So there would be a 7 ohm resistor and there would be a 4 ohm resistor. So between the 7 ohm resistor and the 4 ohm, which one is bigger? Aha, the 7 ohm resistor. Now remember the relationship between resistance and current. So resistance and current are inversely proportional. So where there is a high resistance, if this is high, if the resistance is high, then this guy is low. Vice versa is also true. If the current is low, the resistance is high, and if the current is high, the resistance is low. So when I say that current is divided inversely, I mean that the highest current will flow through the lowest resistor. Okay, I'll repeat that. The highest current will flow through the lowest resistor. Similarly, the lowest current will flow through the highest resistor. So if you look at these two resistors here, 7 ohm and 4 ohm, so there's some current, say I1 and I2, right? So I1 would be the current flowing through the 7 ohm, I2 would be the current flowing through the 4 ohm, and A would be the total current. I'll show you guys why. So A would be the total current, right? So the total current would be um, the ammeter A. And there would be some current that flows through the 7 ohm resistor and current that flows through the 4 ohm resistor. But notice something. The 4 ohm resistor, or rather the 7 ohm resistor, is larger than the 4 ohm resistor. This guy is bigger. And this guy is smaller than the 7 ohm resistor. So that means that through the 7 ohm resistor, that is where I will have my lowest current. And through the 4 ohm resistor, that was where I will have the highest current. Right, so that's what I mean when I say current is divided or split inversely, right? Because these two are inversely proportional to each other. So an increase in the resistance decreases the current, and a decrease in the current increases the resistance. Or similarly, an increase in the current decreases the resistance, or a decrease in the current increases the resistance. So notice how again the 7 ohm resistor, this guy here, is larger than the 4 ohm. So the bigger the resistance, the lower the current. Similarly, the lower the resistance, the higher the current. I hope you guys can see that. So in a typical exam, you must remember, if you're given resistors of different values, right, the higher the reading of the resistor, In parallel, please do not forget that in parallel, we're talking about a parallel circuit here. So the higher the resistance in parallel, the lower the current flowing through it. But the lower the resistance in parallel, the higher the current. And it's true if you have two equal resistors. So let's say you have an 8 ohm resistor and an 8 ohm resistor. They have equal current flowing through it. So if I have these two, if this guy here would be 8 ohms, this guy here would be 8 ohms, these two will register the same current because the voltmeters for starters would be the same, and we'll get to that. So they would have the same voltage, the same current, and obviously the resistance will be different, right? Hold on. Okay, now that we've gotten that part of the way, now we look at voltage. I really hope I was very clear on that part. So remember, current in a parallel circuit is not just divided, it's divided inversely. The higher the reading on the resistor, the lower the current. The lower the reading on the resistor, the higher the current. Okay, so now we're looking at voltage, right? So now we're going to just focus on voltage. So voltage in a parallel circuit is divided, sorry, in a series. Are we looking at the series? Yes, so we're on the series part. So voltage in a series circuit is divided, but not just divided. It is divided proportionally, proportionally. So what does that mean? That means this is why I had said, okay, I'll explain to you now. So remember, sorry. So so you must know that if I will have a voltmeter here for the battery, so that would be V1, and that would be connected to the battery. And then I would have another one connected to R2, so let's call it V2, and then the one connected to R1, let's call it V3. All right, so that would be V3. So every voltmeter has its corresponding resistance. Sorry, has its own corresponding resistor. So what does that mean? So that tells me that, okay, so if that's the case, then the voltmeter across the battery reads the total voltage. You must know that. The voltmeter across the battery reads the total voltage. But what about read 2? Does V2 read the total voltage? No. Every resistor has its corresponding voltmeter. So it has its own voltmeter just for itself and no other resistor. So V2 is for R2, V3 is for R1, and it stays that way. So for V2, the reading on V2 would be dependent on what R2 will be. But when I say voltage is divided proportionally, I mean that the higher the resistance, the higher the voltage. So if I have a resistor, so if I have resistors in series, so if I have resistor and another resistor here, so this guy here will have his own voltmeter, so that's V1, and this one will also have his own voltmeter, so that's, oh, okay, forgot my circle thingy. So that's V2, right? So that's V1 and V2. So if V1 is 12 or 2 ohms rather, and this is 3 ohms, which resistor is bigger? Aha, so you notice that the 3 ohm resistor is bigger than the 2 ohm resistor. Like I said, the bigger the resistance, the higher the voltage. Thus, since the 3 ohm resistor is bigger, that means that its corresponding voltmeter must have a reading greater than the voltmeter for this guy here. So that means that if I have to write that down, I would say that V2 must be greater than V1. Why? Because R3 ohms is greater than R2 ohms. So when I say voltage is divided proportionally, I mean that voltage and resistance are directly proportional. Thus, the greater the reading on the resistor, the greater the voltage across that particular resistor. Similarly, the lower the reading on the resistor, the lower the voltage across that particular resistor. That is why I had this guy here, where I said that voltage is directly proportional to resistance only in a series circuit. Why? That's when we get to this part. So the higher the resistance, so high resistance in a series circuit, so high resistance equals high voltage. So high resistance equals to high voltage. This is why I said that the voltage in a series circuit is directly proportional to the resistance. I really hope you all got that part. Very important part that you must remember. Don't forget that one. Please do not forget it. Very important. It's a very important part, right? So it's very, very important. Please do not forget it. So voltage in a series circuit is divided proportionally, right? The higher the resistance, the higher the voltage. What do you know about current in a parallel circuit? It's divided inversely. The higher the resistance, the lower the current. The lower the resistance, the higher the current. So I do know about voltage in a parallel circuit. So the voltage in a parallel circuit is the same everywhere. So voltage is the same everywhere. So the voltage is the same everywhere, right? Right. And then what do we know about resistance? So if you want to calculate the resistance in a series circuit, so if you want to calculate the resistance in a series, we denote it by Rs for R series. That is R1 plus R2 plus R3 plus dot dot dot. So what would that dot 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 mean? So those dot dot dots just those dot dot dots basically tell me about the number of resistors in series. So if I have one resistor, two resistor, three resistor, four resistor, right? So that means I would have my thing up until R4. The more resistors you have in series, you'll then actually add them there. So there would be R1, R2, R3, up until Rn, depending on how many resistors you actually have in series. Even if you have a million, so there'd be R1, R2, all the way to R million. Don't worry about that. You will never get such a question in the exam. Okay, so how do you calculate the resistance in parallel? So in parallel, the resistance is 1 over Rp. For Rp is resistance parallel, and that's 1 over R1 plus 1 over R2 plus 1 over R3. Okay, that's a B. 1 over B3. Okay, so that's 1 over R3. So that would be R3 plus dot once again. So that would be dependent once again on the number of resistors that you have in parallel, right? And then a very important point that I just want, in fact, I'm gonna have this one in red because it's very important. In a series circuit, please don't forget this, ladies and gentlemen. The more resistors you connect in series, the greater the resistance. So the more resistors in series, the higher the total resistance, the greater or the higher the total resistance. Please do not forget that. The more resistors that you put in series, so the more resistors that you have in series, the higher the total resistance, right? Similarly, the more resistors, so the more resistors you have in parallel, so the more resistors you have in parallel, the lower the total effective resistance. So the lower the total effective resistance, right? So what do I mean? So I'm saying that if you have, so the more resistors you have in parallel, the lower the total resistance. Please, ladies and gentlemen, do not forget these. Very important. The more resistors you have in series, the higher the total resistance. And the more resistors you have in parallel, the lower the total resistance. So if you have more series resistors in series, you're increasing basically, you increase the total resistance, right? So the total resistance will increase when you have more resistors in series. Similarly, the total resistance will decrease when you have more resistors in parallel. So how, I mean, in the typical question paper, you get a question that says resistor R1 was removed, right? So that would be, say they give you a series resistor, and they say resistor R1 was removed, right? How does that affect the total effective resistance? And they ask you, write down increase, decrease, or remains the same, right? So they say to you that resistor R1, which was in series resistor R1 is removed. How does that affect the total effective resistance? Choose from increase, decrease, or remain the same, right? So this will be very helpful in those type of questions. Because you removed a resistor in series, that means you have less resistors in series. That means that you have lower total resistance. So your answer in that particular question would be decrease, because you removed a resistor in series. Thus, you are removing, or rather, you're decreasing the total resistance, right? Please don't forget this. Do yourself, promise me and promise yourself that you will never ever forget this. Please. Okay, then moving on. So if I want to calculate the current in series, now remember that we said that current in series is the same everywhere, right? So that is if I have my positive terminal, which is the long one, and the negative terminal, which is the short one. According to the to conventional current, current flows from the positive terminal all the way to the negative terminal. So current flows in this direction, right? I want you to notice something. Notice how the current flowing through the 2 ohm resistor is equal to the current flowing through the, why am I saying 2 ohms? Sorry. The current flowing through R2 is the same as the current flowing through R1. I really hope you guys can see that. So that means that the current in a series circuit, that is why we say the current in a series circuit is the same everywhere, right? And notice something. Okay, I'm gonna actually do that when I do the next video when we do a few examples on parallel and series circuits. I'm gonna get deeper into that. Okay. So if you want to calculate the total current here in series, you say that total current denoted by I total equals to I1, which is equal to I2, which is equal to I3, right? So the current is equal everywhere. Hope you guys are seeing that. And if you want to calculate the current in a parallel circuit, so remember that current is divided. Yes. So it would be current I1 plus current I2 plus current I3, depending on the number of resistors you have in parallel. Because for every resistor, there would be some current flowing through it, right? Now, if you want to calculate the voltage in series, you say V total equals to V1 plus V2 plus V3. Why? Why do we say that? Because we said that, sorry, just make a young box here. Just love making boxes. Um, why do we say that? Because we said that the voltage is divided, or you could say split, in a parallel in a series circuit, right? So there would be the total being equal. So which one measures the total voltage? Remember, the voltage across the battery measures the total voltage. That guy right there measures the total voltage. And then the voltage in a parallel circuit, what do you think is going to be? Think about it. If you say that the voltage in a parallel circuit is the same everywhere, you should agree with me when I say that the total voltage would be equal to V1, which is also equal to V2, which is also equal to V3, depending on the number of resistors you have in parallel. Oh, what is this? My bad. That was my mistake. So that would obviously depend on the number of resistors you have in parallel. Right. Um, I think we will end it right there for this video. So in the next video, I just want us to go deeper and deeper into these series and parallel circuits. But from me to you, for now, I really hope that everything was clear and no one was lost. And by the way, if you guys get lost, please do actually drop a comment down below, and I'll get back to you as soon as I can. Or you can just reach me on my email address, that is ngidimon 63 at gmail.com. Once again, that is ngidi simon 63 at gmail.com. Right. So, for now, I am going to leave everything in your hands, and I hope that everything was very understandable. I do, I did actually try to explain everything to the best of my abilities, and I hope that everything was clear. But for now, I will leave you guys and hope to see you in another video. Bye bye.